All right, so we're going to do an example now of one of our hypothesis tests with two samples. So in this case, we're going to be comparing the means. We're going to look at the case where you're comparing means from two distributions where you know the standard deviation. I should put standard deviations for each population. This is a bit unrealistic, and you'll see my example is a bit contrived, but we're just going to start here. We're also in the case where we have independent samples, meaning the samples, we'll assume both samples chosen are random samples, and that there's no dependence between them. Who I choose in one sample doesn't affect who I choose in the other sample, right? You can have when you do have paired samples, it can be something like testing people, exposing them to a treatment, and testing them again for some characteristic, right? So the populations in each distribution are not independent. In that case, they're the same. But you can have other dependencies. So in any event, in this case, just imagine random people. There's no choice for one population, or one sample makes any difference to the choice in the other one. So that's the case we're in. So this is what we're going to do, is what you're going to be tasked to do once we go through all the different examples, right? Is categorizing the situation, and then you just apply the formulas that we're going to go through. So what we're going to be looking at, we will have two distributions, x1 and x2, that we're interested in. If we have large samples, or if x1 and x2 are approximately normal distributions, we're gonna choose samples. I'll call them little x1 bar and little x2 bar. And remember, we're comparing them, and so what we're going to be looking at is the difference between these. Right? That's just kind of the process that's in our heads, that's happening behind the scenes. That we create a new sampling distribution when this happens. I've been calling this D for the difference distribution. When the conditions that, again, like I said, if x1 and x2 are approximately normal, or if our sample sizes are large, meaning the sample sizes for x1 bar and x2 bar, then this difference distribution will be normally distributed. Its mean will be the difference between the means of the original distributions, right? Mu1 would be the mean of x1, and mu2 would be the mean of x2. And the standard deviation of this distribution would be the standard deviation of x1 divided by the sample size for x bar 1, and standard deviation of x2 divided by the sample size for x bar 2. Okay, that's the distribution we get. And the test statistic that we compute will be a z-score, right? Because we're dealing with the normal distribution. And the z-score is computed in the following way, right? It's really the same as that we've done in the past, right? Let me write it over here, right? When we were doing hypothesis tests with one mean, we would have a sample mean minus the mu divided by our standard deviation. Right, the standard deviation from the original distribution divided by the square root of the sample size. It's the same idea, right? This piece right here is our sample mean, right? But now we're doing a sample difference of means, so we get x bar 1 minus x bar 2, right? That's playing the role of this orange circle up here, and then we subtract from it the mean of the distribution. Right. Well, in this case, so we're subtracting the mean of the distribution. We're doing the same thing here. It's just that our mean now looks like this: mu1 minus mu2. Right. And then we're dividing by the standard deviation. Right. This is the standard deviation that the central limit theorem tells us. And here we have this slightly more complicated version, but it's the same idea. So there's nothing. It's new, but it's very much in the same pattern as we've been looking at, right? And that's what it'll look like. And that'll be our test statistic. Typically, this value will be 0, because typically our null hypothesis is that mu1 and mu2 are equal. So not necessarily always, but very typically that will be the case. Um, and so that piece will end up disappearing. Um, but in any event, this is what it looks like. Once we do the test statistic, depending on how you want to go, you can either use the critical value method, right? What's the z-score associated with the level of significance for your test, or you can find the p-value and compare it to the level of significance. So there's the setup. Let's go ahead and do an example. So I've typed up an example here. We've got a company that believes a new website design increases the time the visitors spend on their site. A study exposes the new and old sites to random samples of people and records the time they spend. A sample of 53 people was exposed to the new site and spent an average of 7.5 minutes on the site. 49 people were exposed to the old site and spent an average of 7.1 minutes on the site. Test to a 0.05 level of significance. The claim that the average time spent on the site is greater with the new design. Assume the standard deviation for the population of people who use the new design is 1.1 minutes, and the standard deviation for the population of people who use the old design is 1.3 minutes, right? So that last part is the part that's fairly contrived and unrealistic, but let's just go ahead anyways just to get a sense of this process, right? So the first thing I'm going to do is just collect information, right? For the people who were exposed to the new site, right? I'm going to consider the population of people exposed that would be exposed to the new site, this distribution x1. We got one sample of them, right? So we have a sample. The sample size is 53 people. And the sample mean was 7.5 minutes. I'm going to leave units off to keep this simple over here. And I'm going to list it here. The standard deviation for this original distribution is 1.1 minutes. Okay. For the old site, right, we can imagine has some distribution associated with how much time people spend on it. The sample size there is 49. The sample mean time spent on the site is 7.1 minutes. And the population standard deviation, oops, I'm writing the wrong subscript, was 1.3 minutes. Okay, so I'm just translating everything from the words into, I'm just kind of laying it out so I can just have the pertinent information, right? Let's go back for a second, because really what we need to do is compute this test statistic, right? This piece of the puzzle, the distribution, right? That helps us understand why this works, but in practice, we don't need to kind of go through that part. I just need to compute this test statistic. So let's go ahead and do this. I'm just going to plug the values I got into this. In fact, let's just grab this guy. If I can do it without grabbing everything. I think I know how to do this. Oh, it didn't work the way I thought it used to work. It's been a while, so I'm just going to leave it alone. So in any event, we're going to plug our values into that, right? So here we're going to have, let me grab a pen. There we go. Our z-score is going to look like, so first we take the difference of the sample means, 7.5 minus 7.1. Oh, sorry, I forgot to do my hypotheses. I got to set those up. So the null hypothesis in this case could be that the difference in the means is 0, right? There's no difference. The new site doesn't do anything to increase the time people spend on the site, okay? And the alternative is that the difference between the means is positive because, right, mu1 is the mean under the new site, and our hypothesis that we're testing is that it increases the amount of time people spend there. So if mu1 is greater than mu2, their difference will be positive. So there's our hypotheses. Now we compute just a test statistic. Sorry, I jumped ahead in my notes before. So we've got the difference in means, Here, let's write it out one more time. It's going to look like this. X bar 1 minus X bar 2 minus mu1 minus mu2 all over the standard deviation of the new distribution, which looks like sigma 1 squared over n1 plus sigma 2 squared over n2. So for us, this is going to look like 7.5 minus 7.1, just copying from our up above, minus 0, because we assume, right, this is the same thing we do in our hypothesis test with single samples. We assume our null hypothesis is true, which means the difference between the means is equal to 0. So that piece of the puzzle goes away. It's a 0. So I can move on to the denominator. We get the square root of sigma 1 squared, so 1.1 squared over the sample size of the first sample, 53, plus 1.3 squared over the sample size, 49. So obviously that's a calculator problem, and I worked that out to be rounded to 1.67. Okay? So there is our test statistic. Okay? And now we're testing this like any other, right? It doesn't matter at this point that we started out with 2 samples. It's just like any other hypothesis test. We've got our test statistic. I'll just rewrite it here. Z is equal to, what did I just say? 1.67. And we're testing to a significance level of 0.05, right? So there's 2 ways we can proceed. I can compute using a normal distribution calculator the probability that Z is greater than or equal to 1.67, right? This is going to be a right-tailed test because we're testing that the mean is greater. And so I plugged that in, and I got 0.0475. We can also look at the critical value for alpha of 0.05. The critical value is 1.64, right? So in either case, right, we can note that 0.0475 is less than 0.05. In other words, the p-value is less than alpha. Or we can note, if we imagine what our normal distribution looks like, right, our critical value, let's just put it here, 1.64. We got a value above that, 1.6, what did I say, 67. And so I know that, let's change colors. This red area, oops, I thought I grabbed red. This red area is smaller than the total area above 1.64, right? In either case, we've determined that our test statistic shows us that what happened in our sampling was more rare than we would expect from just a random aberration, that it implies something significant. In this case, we would reject, my pen is not quite working right anymore. But anyways, I think I just have to slow down. We reject H naught. We believe the new site increases the time, the new site design increases the time, oh my God, this is terrible, it just keeps jumping, time spent on the site. Okay. All right, so there it is. And this is one of the examples, but I just want to again reiterate, we are just, it's very similar to what we've done in the past, right? You got to categorize when we had single samples. Do I know the standard deviation of the population or not? Am I looking for a proportion? Then you know which of the 3 methods we previously discussed to use. We're just adding a new kind of upfront question. Am I dealing with a comparison of means? And if we are, then we start looking at, do I know the standard deviation from the 2 populations? That's what we just did here. We'll look at when we, and we also have to know, are our samples independent? And then if our samples are independent, we can either know the standard deviation for the populations or we can't, and then we have two different tests. Same as before, when we know the standard deviation for the population, it's a z-score. When we only know the standard deviation for the sample, we'll do a t-score. I'll do that in the next example. Okay, that is it for this one.